to the Sustainable Engineering Concept and Life Cycle Analysis tutorial 2. I am Sagarika Panigrahi, a research scholar and TA for this course. Today I am going to do few problems related to global warming potential, material flow information and dose base relationship. Let us go to the first problem. The first problem is related to global warming potential and the question is the list of global warming causing gases released from a metal processing industry is given in the following table. Determine the global warming index for the metal processing processes and the percentage contribution of each chemical. The chemicals given in this problem are trichloroethane, carbon dioxide and nitrous oxide, and the emission rate are emission rate is the rate at which pollutants are emitted from the source per unit time, and it is generally expressed as mass per unit time, that is kg per hour. And in the question it is given that it is 15, 7000 and 0.2, and the global warming potential of each pollutant is 100, 1 and 298. Then the global warming index of each pollutant is emission rate multiplied by the global warming potential, that is 1500, 7000, 0.2 multiplied by 298, that is 59.6. Then the total global warming index of the whole process is the summation of these, that is 8559.6. This is the solution of our first part, that what is the global warming index for the metal processing process. Then second part is the percentage contribution of each chemical, that is percentage contribution of each chemical, that is contribution of each chemical divided by total global warming index into 100. Here for trichloroethane, this is 1500 divided by 8559.6. Here we are expressing in terms of percentage, so multiplied by 100, that is 17.52 percentage. For carbon dioxide, it is 7000 divided by 8559.6 into 100, that is 81.77 percentage. For nitrous oxide, this is 59.6 divided by 8559.6 into 100, this is 0.7 percentage. This is the solution of our first part, first question. This is global warming index of the whole process, and this is the individual contribution. Let us go to the second question. Second question is based on material flow information. This material flow information is an application of conservation of the mass of the physical systems. As per law of material flow balance, suppose this is a boundary, there are inflow, there may be more than one, and there are some outflow. There may be some generation inside the boundary and there may be some accumulation inside the boundary. According as per law of material balance, that input plus generation must be equal to output plus accumulation. The question number problem, the problem to which material flow information of the type shown in the following figure typically comes from multiple sources, and material balances can be used to assess the consistency of the information, determine whether the flows in the following figure satisfy a material balance. So, in this figure the input is only 694 teragram per annum, and the output is 212 teragram per annum, and the accumulation inside the system is, that is stock, this is 481 teragram per annum. In this question there is no generation inside the boundary. So, the input output relation we can write as that input is equal to output plus accumulation, that input is 694 and the output is 212 plus accumulation is 481, this is 694 and this is around 693 teragram per annum. So, within rounding error the flow satisfies the material flow balance. Then come to problem 3. The maximum average annual concentration of benzene in the ambient atmosphere of a city is 82 microgram per meter cube. Calculate the inhalation dose of benzene for the following exposure. These are the properties, that average body weight is 70 kg and air breathing rate is 19.92 cubic meter per day, and the ABS, that is absorption rate of inhaled air, is 1.0, and EF, that is exposure frequency, is 365 exposure days per year, and ED is exposure duration, that is 70 year, and AT is average time, that is 25,500 days. So, suppose this is the emission rate and the ambient concentration of benzene is C is 82 microgram per meter cube. Suppose this is a human being. This is the ambient concentration of benzene, that is 82 microgram per meter cube, and these are the exposure properties, and the average body weight is 70 kg and air breathing rate is 19.92 meter cube per day, and the ABS, that is absorption rate, is 1.0, exposure frequency is 365 days per year, and the exposure duration is 70 year, and the average time is 25,550 days. So, as we have already discussed in week lectures and in assignments also, that dose is generally expressed in terms of kg of or weight of pollutant per body weight per day. The kg of pollutants means that weight of weight of benzene, that is ambient concentration multiplied by breathing rate multiplied by exposure frequency multiplied by exposure duration multiplied by absorption divided by body weight into average time. Ambient concentration is 82 microgram per meter cube, and breathing rate is 19.92 meter cube per day multiplied by exposure frequency, that is 365 days per year multiplied by exposure duration, that is 70 year, multiplied by absorption, that is 1.0, divided by body weight is 70 kg, multiplied by average time, that is 25,550 days. So, here meter cube got cancelled, this days and days, year and year. So, this will be 23.334 microgram of benzene divided by kg of body weight per day. Okay, let us come to the question number 4. The question number 4 is on dose based response relationship. The previous question was on dose, then this question will help you to have a clear understanding on dose based relationship. Determine the inhalation carcinogenic risk for an inhalation dose of 0.03 milligram hexavalent chromium per kg body weight per day, and the carcinogenic slope factor for dose response relation is 2.9 in 10 to the power minus 2 milligram hexavalent chromium per kg body weight per day. So, in the question it is given that the inhalation dose is 0.032 milligram hexavalent chromium per kg body weight per day, and slope factor for dose response inhalation is, and the slope factor is 2.9 into 10 to the power minus 2 milligram of hexavalent chromium per kg body weight per day, whole inverse. Then the inhalation risk is inhalation dose multiplied by slope factor, which is 0.032 into 2.9 into 10 to the power minus 2, that is 9.28 into 10 to the power minus 4, and it is unitless. Okay, then come to the question number 5. Question number 5 is each year approximately 5,000 persons lose their lives in vehicular accident in West Bengal. Population 91.3 million according to the 2011 census. Then how many fatalities would be expected over a 3-day weekend in Kolkata area for a population of 4.5 million? So, in this question, suppose this is West Bengal and this is Kolkata and this is West Bengal, and its population is 91.3 million is population, and its vehicular accident rate is 5,000 person per year, and in Kolkata its population is 4.5 million, which is population, and the fatality rate over a 3 weekend days means number of persons per 3 days we have to determine. Here we have to assume one thing, that the death rate pattern in West Bengal is similar to that of the Kolkata. So, the So, the fatalities that can be expected over a 3-day weekend in Kolkata area can be calculated by using the given equation. The equation is approximate persons lose their life in West Bengal over a 3-day weekend divided by total population of West Bengal multiplied by population of Kolkata. Here the life should be in terms of 3-day per weekend, but here we have per year, we have to convert that into 3 days, that is person per year, we have to convert that in, that is year for 3-day weekend. Divided by total population, that is 91.3 million, and it should be multiplied by the population of the Kolkata, that is 4.5 million. So, this will be 2.02 person per 3-day, but in real life we can't imagine that, can't say that 2.02, that should be 2 person per 3-day weekend. Okay, this is all about problem 5. Let us come to the problem 6, that is determine the efficiency of energy utilization for a pump. Assume the following efficiencies in the energy conversion, that crude oil to fuel oil is 90%, fuel oil to electricity is 40%, electricity transmission and distribution is 90%, conversion of electrical energy into mechanical energy of the fluid being pumped is 40%. In industry, we operate a number of mechanical units. The overall efficiency of all units is needed to be calculated to determine the process feasibility. In the question, the first efficiency given is that crude oil to fuel oil, that is 90%. Then second is fuel oil to electricity, that is 40%. Then third one is electricity transmission, and distribution, that is 90%. Then the fourth one is conversion of electrical energy into mechanical energy of the fluid being pumped, that is 40%. Then the overall efficiency is multiplication of individual efficiency, that is overall, that is O for overall efficiency 1, 2, 3 and 4, that is 0.9 into 0.4, 0.9 into 0.4, that is 0.13, that is in terms of percentage, that is 13%. This is the solution of problem 6. Then let us go to the problem 7. This is the solution of problem 6. Let us go to the problem 7, that is estimate control cost for greenhouse gases for an electricity generating unit EGU as a percentage of sales revenue. Assume that the EGU uses coal as fuel and converts the heat of combustion of coal into electricity with 35% efficiency. The heating value of coal is 23,260 kilojoule per kg. Coal is 85% carbon. Carbon cost 12,000 rupees per ton to capture and sequester, and electricity can be sold for 60 rupees per kilowatt hour. So, in the question, first we have to determine control cost for greenhouse gases in terms of percentage of sales revenue. So, please notice that that here we have to determine control cost in terms of percentage revenue, and the first assumption is the EGU, and the first assumption is coal. The EGU uses coal as fuel and converts the heat into combustion with efficiency of 35%. Then the efficiency is 35%, and heat value of coal is 23,260 kilojoule per kg, and carbon content is 85%, and selling price of electricity is 60 rupees per kilowatt hour, and the carbon capture cost is 12,000 rupees per ton of carbon. Just remember one thing, just here is 12,000 per ton of carbon, and here we have coal. So, we have to convert the coal in terms of carbon, that electricity generation per ton of electricity generation per ton of carbon is our total. Here we are using 1 ton of coal, and its content is, and carbon content is 85. So, we have to multiply 0.85, then multiplied by here it is ton, here I am converting it into kg, that is 1000 kg per ton, multiplied by heating value of the coal, that is 0.00003845 kilowatt hour per kilojoule, multiplied by 23,260 kilojoule per kg, with 35% efficiency, that is 2,660 kilowatt hour per ton carbon, and the control cost is 12,000. So, the control cost are 12,000 rupees for 2,660 kilowatt hour per ton carbon, and the revenue collected from the whole process is 2660 multiplied by 60, that is 1,59,600 rupees, and the control cost is how much times. Here we have to determine the control cost for greenhouse gases for an electricity generation as a percentage of sales revenue, that is 12,000 divided by 1,59,600, here percentage, so I am multiplying 100, that is 7.5%. This is all about tutorial 2. Thank you.